Baksa과정, a PhD student of SEM Lab, advised by the Professor Ji.
No.
Sorry. Today my report topic is about the influence of the joint and foundation flexibility on the dynamic response of the jacket of the wind energy structures. I will briefly introduce it from the following three parts. It's well known that the numerical analysis program is a very important tool in the design and the analysis of the offshore structures. However, it involves the coupled analysis of the multiple models such as the aero die, surf die, elasto die, and hydro die, and sub die, even the foam die, and as well as the mode die in the flexible in the floating structure analysis. Also, there are many numerical analysis programs. They still have some limitations. In here, we compare the commonly used program in terms of the various dynamic models and the function in the US and FLS analysis, also the rigid motion and hydroelastic analysis, and the GOA and pre-post proposal. And we can see most of the programs still limited in some aspects. So based on the X-Wind program, we make some improvement. But today we only focus on the limitations in the simulation of the jacket of the structures. That is the foundation flexibility effects caused by the local joint element as well as the foundation models. As shown in this table, we can see most of the programs just assumes the local joint as the rigid one, and it ignores the local joint deformation. And also for the foundation models, most of the program just assumes the fixed foundation or just use a simplified coupled spring model or apparent fixed length model. So based on the X-Wind program, we built these three different joint elements and also 4 different foundation models, and then compare their performance. I will make a brief introduction to the local joint flexibility and the foundation flexibility. As we know, for the big structures like the offshore wind turbine, if we use the shear element or the solid element, it will take a lot of times. So in general, we will use the frame element in the analysis. But you know, as I stated before, for the frame element, most of the program, it will use the rigid element in the local joint. It will ignore the local deformation between the cord and the brace. So, some researcher developed the C2C element, just assign the brace property to the local joint. But you know, the brace also have a large stiffness, so it will also lead to some considerable numerical errors. So in here, we developed the local joint flexibility element, use a flexible stiffness matrix to better reflect the cord brace deformation. Also, for the foundation flexibility, you know, if we want to simulate the slope behavior, we have to use the solid model. But you know, it will take a long calculate time. So most of the research just use a fixed foundation or just use a simplified foundation models. Maybe use equivalent coupled spring model or use a bigger stiffness foundation pile to represent the Pearsall system. But you know, such assumption or the simplification will cause the numerical errors in the finite element analysis. So we developed the local joint flexibility element and the DNS model in the Xwind program. This is the developer progress of the blockchain element in the Xwind program. First, we need to calculate the blockchain flexibility according to the equation given in the DMV code, or just measure from the experiment. Then we need to make a flexibility transformation between the chord and base and chord coordinates. When we make a flexibility transformation, we can get the stiffness of the constraint system. Then, according to the force equilibrium, we can drive the force stiffness matrix. And the last step, just make a transformation from the local coordinate to the global coordinate. And for the PSI model in the Xwind, it's easy. We just need to define the PY curve and TZ curve and the QZ curve. And the last is the case start. In here, I select the NIL 5 megawatt jet offshore wind turbine as the reference model, and select the DLC 6.81 as the design load cases. This is the environmental conditions. And this is for every model developed in the Xwind. We use the 4 different foundation model. Also consider the local joint flexibility. And this is the result. From this, in here, we just discuss the dynamic response in the natural frequency and the displacement and also stress. First, we see the rigid. If we use the rigid element and the fixed foundation model, for this model, it ignores the flexibility of the joint and the foundation, so it will make our estimation of the structural stiffness. So it will result in increase the natural frequency and stress and decrease the displacement. In here, we can see for the rigid and fixed foundation model. In here, we can see it has a largest natural frequency and also the maximum stress and also the smallest displacement. And for the local flexibility and distributed nonlinear spread model, we can see this model consider both joint and foundation flexibility. We can see the blue one, and it has the smallest natural frequency and also the small stress, but have a large displacement. We can see. We'll close the blockchain flexibility and foundation, fixed foundation and rigid and distributed nonlinear spread model. It only considers one aspect of the flexibility. We can see the dynamic response line between these two models. So we can conclude that the consideration of both joint and foundation flexibility is very important in the dynamic response analysis of the jacket structures. That's all. Thank you.